Hi all, my name is Jamie Tayar and I'm Hubble postdoctoral fellow here at the Institute for Astronomy in Hawaii. And I'm going to talk to you today about the evolution of intermediate mass stars. And I'm going to hope to convince you in this talk that even though I work on lower mass stars than most of you, you should still pay attention to and be interested in my talk. And specifically, I'm going to argue that these sort of 2 to 3 solar mass stars form an excellent bridge between the low and high mass regimes, where they become red giants, so they're amenable to the detailed photometric, spectroscopic, and asteroseismic characterization that we've been able to use for lower mass stars. But they give us insights into the evolution of more massive stars that can be used to make predictions for things like rotation, activity, and mixing. So to kind of anchor you, I'm going to show this is the evolutionary track in luminosity and effective temperature for a 2.6 solar mass star. So you can see stars start out on the main sequence, burning hydrogen into helium in their cores in pink. And in this regime, they have convective cores. Like more massive stars, they rotate rapidly, they evolve relatively quickly. And then they eventually exhaust the hydrogen in their cores. They quickly cross the Hertzsprung gap and evolve up the red giant branch, where they reach the tip of the red giant branch and are able to non-degenerately ignite their helium, where they then contract back down to the core helium burning phase and then evolve up on the asymptotic giant branch. Now, in this sort of red giant regime, they develop convective envelopes, they start to pulsate more like solar-like stars, and we can use those solar-like oscillations to do detailed characterization of their interiors. So hopefully Lisa gave you a much more detailed explanation of the solar-like pulsations and oscillations. But just as a refresher, remember when you look at the light curves of these sorts of stars, these red giant stars, you see that they're not in fact flat, but they're variable, even if they don't have obvious star spot modulation. If you take the Fourier transform of that variability, you see this sort of characteristic power spectrum, power as a function of frequency, where at high frequencies, you're seeing instrumental noise. At low frequencies, you're seeing the effects of convection and granulation. And in the middle, you have this regime where you're sensitive to the stellar oscillations. And if you zoom in on that regime, you see the sort of characteristic Gaussian peak with a characteristic frequency that we refer to as the frequency of maximum power, mu max. And then if you look carefully at that, you see this sort of characteristic picket fence of regular spacings of oscillation modes, separated by some characteristic frequency that we refer to as the large frequency spacing. Now it turns out that the mean density of the star is related to that characteristic frequency spacing, and the surface gravity of the star is related to the frequency of maximum power. So if you combine these two pieces of information together, you can get an independent estimate of the mass and radius of isolated stars. And then if you look in even more detail at these pulsation modes, you can learn things about the rotation of the region where that mode is spending its time, which is often the cores of these stars, and other detailed physics of the stellar interior, including distinguishing between core helium burning stars and stars that are still shell hydrogen burning. Okay, so if we go back to this anchor diagram, I'm going to have this on every plot so that we know where we are on the HR diagram. And I'm going to start out talking about these sort of main sequence stars that you're probably more familiar with. So for each of these regions, I'm going to tell you about the surface rotation, core rotation, activity, and mixing. We're going to start here with the surface rotation. So these 2 to 3 solar mass stars are more like massive stars here in this regime. They're rotating relatively rapidly with a range of rotation velocities that goes up to something like 300 kilometers a second, but is well distributed. Now the core rotations of the regime, we don't have a ton of core rotation measurements above 2 solar masses. So this is a diagram for stars slightly below that mass range. But at least in that regime, we see that this core rotation frequency or core rotation rate of these stars over their surface rotation rates is something close to 1. So that means that the core and the surface are rotating at almost the same rate. So for now, we're going to assume these stars are rotating pretty close to rigidly. Now, if you look at the activity in these stars, with the grad student Ellis Avalon here in Hawaii, we've been looking at variability in test light curves, mostly for lower mass stars, but this is one of the stars in a sample that's close to 2 solar masses. And you see this is one of the only ones where we see anything that looks even remotely like rotational modulation. So at the very least, most of these stars are not rotationally active in the way we see in lower mass stars. Now, in terms of mixing, well, so the apogee survey is one of the spectroscopic surveys I'm going to talk about a little bit later. And we are mostly focusing on taking spectra of lower mass stars across the galaxy, including mostly red giants. But to do that, we take telluric standards, and notice most of those are A stars. So that means we actually have quite a sample of sort of A-ish type stars, where we've taken a number of spectra. And so Drew was able to use that to point out that, at least in our sample and other known samples, the chemically peculiar stars, in this case mercury manganese, is correlated with the rotation velocity. So at least some of these chemical peculiarities can be correlated with other tracers that we're interested in terms of rotation, activity, and mixing. Okay, so then we're going to move along to the red giant branch, where maybe you're less familiar, but we're going to talk in the same way about the surface rotation, co-rotation, activity, and mixing of the stars on the red giant branch. So let's start again with the surface rotation rates of these stars. And given that we know what their distribution of surface rotation rates is on the main sequence, and we know that their rotation is relatively rigid, so we can assume the core has the same rotation rate as the surface, we can make a prediction of how the surface rotation periods of these stars should evolve as they evolve in time. So here their envelopes are expanding. That means their radius is increasing. That means the moment of inertia is increasing. That means the star should be slowing down. And then on top of that, we think these stars have developed convective envelopes, which means they should be able to drive the same sort of magnetized winds that we see in lower mass stars. So they should be slowing down even more than angular momentum conservation would predict. Now, these stars had a range of rotation rates on the main sequence, and we expect that range of rotation rates to persist onto the red giant branch. And so what I'm showing here is a band of prediction expectations given the range of rotation rates that we see on the main sequence. This is for a 2.2 solar mass star, where you can see it's crossing the Hertzsprung gap and then evolving up the red giant branch, and the same for a 3 solar mass star, that same sort of shape. And then I can add data to this plot of stars with known surface rotation periods, in this case from Patrick Golm, but there are a couple of other surveys as well. And in general, it looks like, at least on the lower mass side, that these seem to be more or less following the predictions that we're making, where you see this range of rotation rates at fixed mass and log g, which makes sense given the distribution that we see, and we see it evolving over time. Now, on the right side of this plot, you've probably noticed a couple of the points that are rotating much faster than our models would have predicted. Now, I would argue that many of those are the results of interactions, where they've interacted with a companion, gained angular momentum from that interaction, and spun up, because I'm a very strong believer in angular momentum conservation. But in any case, there were some clear detection edges, and mergers might be important in this regime, but we can at the very least measure surface rotation rates. Now, core rotation rates in this regime can actually be easier to measure than surface rotation rates because the core rotation causes an obvious splitting in the oscillation modes. So here I'm showing again the same models of what I think the surface rotation rates are doing. And then I'm plotting here data from the literature of what the core rotation periods that have been measured for stars in this mass range are. And you can see that they're substantially faster than what we think the surfaces are doing. And there don't seem to be any strong trends with mass or surface gravity. Okay, so what about activity in these stars? Well, we know that there is activity because we were able to measure the surface rotation rates. But one of the other things Patrick Golm noticed was that he did a plot of the oscillation strength, which is the y-axis here, as a function of nu max, which is an evolutionary coordinate in this regime. So stars are evolving from right to left on this plot. Now, most of the stars, which are plotted in gray, follow this sort of characteristic relationship between the strength of the oscillations and the frequency of maximum power, or the evolutionary point. However, if you look particularly at the active stars, which are marked here in red, you see that there are substantially weaker oscillators than otherwise would have been predicted given their evolutionary state. So it looks like activity reduces oscillation strength on the red giant branch. And finally, mixing. So as these stars are evolving in the red giant branch, they're developing surface convection zones. These convection zones are getting deeper, and they start penetrating into regions that have been affected by nuclear processing. And those regions tend to have more nitrogen and less carbon because of the CNO cycle. So that means when the convective envelope penetrates to that depth, it dredges up that material to the surface, and we see a change in the surface abundances in carbon to nitrogen ratio. Now in lower mass stars, the depth of this first dredge up is strongly correlated with the mass of the stars, and so we see in the density of points here a strong correlation between carbon to nitrogen and mass. However, if you look into the sort of 2 to 3 solar mass regime, you don't see that strong correlation anymore on the red giant branch. But what you do notice, if you add all of the stars where we have rotation modulation and activity, is that those stars seem to be on the more mixed side, lower carbon to nitrogen, than kind of the full range of these more massive stars. Now, obviously, there aren't a ton of points in this circle, so this is still pretty tentative. But at least it's possible that there's a correlation between rotation and activity and mixing in this regime. Okay, so now we can move on to the core helium burning phase, which is where stars spend much more time on the red giant branch in this mass range, which allows us to get much more statistically significant samples. So we'll start first with the surface rotation rates of these stars. And if you would ask 10 years ago what the surface rotation rates of these stars should have been, people would have told you that they should have been relatively rapid. Where stars are rotating between like up to 10 or even 20 kilometers per second, which should be easily measurable with current spectroscopic surveys. However, that was using a more traditional angular momentum loss law, and recent work has suggested that we need a more sophisticated angular momentum loss law that specifically parameterizes the angular momentum loss as a function of the convective overturn timescale, the luminosity of the star, the photospheric pressure, and so on. And when we look at the data of the distribution of surface rotation rates in this regime, we see that indeed we do need that more sophisticated treatment of angular momentum loss if we're going to match the distribution that's actually observed. Okay, so what about the core rotation rates in these stars? Well, again, we can measure the core rotation rates using asteroseismology. And so I'm plotting here the core rotation period as a function of surface gravity, where stars are evolving from left to right on this plot. In the blue band, I've got the predictions for those same models of what the surfaces should be doing in this regime. And you can see that the black points for the core rotation rates are a little bit higher than what we think the surfaces are doing. The cores are rotating a little bit faster than the surfaces, although they do seem to be evolving with surface gravity, which means that the core is aware that the envelope is expanding, which means there must be some substantial amount of angular momentum transport in this regime. So in terms of activity of these stars, when Patrick Gaume was looking at the samples, he noticed that on the red giant branch in this more massive bin, so the rightmost bin on this plot, that more than half of the RGB stars seem to be active. And that fraction is cut almost in half on the core helium burning phase. But if we think about the fact that the rotation and activity should be correlated, and we know that these stars are losing angular momentum in this phase, then they should be slowing down, and that means they should be less active. So perhaps this all hangs together quite nicely, whereas these stars are less active on the red giant branch, which makes sense given the way they're rotating. So finally, in terms of mixing, we can look again at this same sort of relationship between the carbon to nitrogen rate, the carbon to nitrogen ratio and the mass of these stars, where again, the low mass stars are less mixed, and we can see that the trend continues at least to 2 solar masses and perhaps even further. But now when we plot the stars that we see as active, we don't see any strong difference in this 2 to 3 solar mass regime between the stars that are active and the underlying sample. So it looks like, at least here in carbon to nitrogen, and the few places that I've checked so far in lithium, which should be a more sensitive diagnostic of mixing, we don't see any strong correlation between the core rotation rates, the surface rotation rates, and the mixing diagnostics. So, in summary, I hope I've convinced you that the 2 to 3 solar mass regime is a really interesting one for bridging the gap between low and high mass stars. We can do detailed photometric, spectroscopic, and astroseismic characterization of the sample, which allows us to learn about the physics of things like rotation, angular momentum transport, loss, activity, and mixing, which hopefully gives us some physical insights that can then be applied to the models of more massive stars that you might be more interested in. So thank you for listening, and I'll take any questions.